All right, so today we are talking about stoichiometry. Primarily, it's all we're going to get through today is stoichiometry. I know many of you did this in high school. If you didn't do it in high school, now you're doing it today. All right, so just a reminder, because I see students do this a lot during stoichiometry calculations, and I want to make sure you don't do it. You never, ever, ever use Avogadro's number in stoichiometry, okay? Because Avogadro's number, 6.022 times 10 to the 23rd, is used to calculate number of particles, number of atoms, number of molecules, right? We're not going to be doing those kinds of things in stoichiometry calculations. And just a reminder, when you're dealing with mass, right? If I gave you a mass in grams, right? The conversion factor that we use there is molar mass, which comes from the, where? Where do we get molar mass? Periodic table, right? Okay, so we talked about moles a couple weeks ago. We did molarity a couple weeks ago, so you could use that skill in lab. And now we're going to take it further. So who cares about moles? Okay, so I've got something for you to consider. I'm actually going to turn the projector off. And turn my camera over here. All right, so I'm going to do something for you to think about today. I'm going to get gloved up. Actually, going to get double gloved up because I want to be extra careful. It's probably not necessary to wear 2 pairs of gloves, but I'm just chemophobic, I guess. What can I say? So this is the solution that I prepped earlier. Getting them in here because they're light sensitive. It's not because it's a surprise, just light sensitive. And this is just hydrogen peroxide, like what you get at the pharmacy. I'm going to put on a scrape. It's going to act as our catalyst. All right, so catalyst is just something that speeds up the reaction. I hope this is working on the camera. I'm going to turn off the other bank of lights. Ooh, scary. All right, are we ready? 3, 2, 1. Woo. It's almost October. This is appropriate. So this is called chemiluminescence. It's when a reaction produces light. And this reaction, it will stay like this for a long time. Can you think of chemiluminescence in nature? What comes to mind? Fireflies, right. And that's a really common thing that comes to mind. If you think of the cover of your lab manual, right, that picture of the blue glowing on the cover of your lab manual, that's this same reaction, just a picture of it. It's just a slightly different color. Right, but this is a chemiluminescence reaction. And it'll actually continue for several minutes. All right. So, as we talk about today, let's ask ourselves some questions. Gotta get everything fired back up again. What information would you need to replicate that experiment? If you wanted to go home and do this experiment this weekend for your friends, what information would you need to replicate that experiment? What kind of info would you need there? You'd need to know the identities, right? You need to know what it is, probably where to get it too, right? I should probably wash my hands while the projector's firing up. You need to know the identity. What else would you need to know? The quantities, right? You need to know the quantities, you need to know the identities, you need to know a balanced reaction, right? So you know what you're producing. Is there anything else that you would need to know if you were going to replicate that experiment? The what? Okay, yeah. How to properly protect yourself, right? All of these are all things that you would need to know if you were going to do this, right? How much reactant, how much product am I going to make? How long will it last? That's actually a question we'll answer next semester in Gen Chem 2. Is there any energy release in the reaction? So stoichiometry answers all these questions except how long. Okay, you can't do how long with stoichiometry. That's a kinetics calculation. And it's kind of a stretch to say that stoichiometry can give you how much energy is produced either, because that's really more of a thermochem question. But we'll be able to answer that in a couple weeks. So stoichiometry answers all these questions for us, with the exception of how long. And it's kind of stretching it to say stoichiometry could answer how much energy. But nonetheless, stoichiometry is a set of calculations, okay, that we can do to figure out how much reactant we would need in order to make a general product of a certain size, or vice versa. If we had this much product, how much reactant did we begin with? Okay, so we have to have a balanced chemical equation. Has to be balanced, okay, because these coefficients represent the mole ratios between the reactants and the products. So 2 moles and 1 mole producing 2 moles, okay? So the mole ratio tells us the coefficients tell us the mole ratios. So here are the steps in stoichiometry. If you've never done this before, you'll do it now. And if you have done it and you're an expert, then you can just kind of refresh your memory. You're going to convert grams of your starting material into moles, unless it's already given in moles, which it won't be, unless we're doing molarity calculations. But we're not doing that today. We're going to multiply by the mole ratio from the balanced equation. So this will give us moles of the material that we're finishing with. And then we're going to convert moles of that finishing material to grams, which is usually what the problem asks for. Unless we start doing solution stoichiometry, and then it'll be slightly different. But we're not doing solution stoichiometry yet. And just so you know, stoichiometry can be used to find out information about the reactants or the products. So in other words, you can use information about the products to work backwards to the reactants, figure out how much you needed to begin with, or you could figure out, okay, if this is how much reactant I have, how much product can I make?
Second step is mole ratios, coefficient.
Yes, the coefficients from the balanced equation. So if you did this in high school and you already remember it, awesome. It's just a review. And if you didn't do it in high school, we'll get you caught up today. Grams to moles, mole ratio, and then moles back to grams. Those are the 3 steps. Okay, so here it is in picture form. To convert grams to moles, right, that's using molar mass. That's not using Avogadro's number. Mole to mole ratio, that's just the coefficients. And then moles back to grams, again, using molar mass. So make sure you know you're not using Avogadro's number here. Your answer will be really, really wrong. Okay, so this is an experiment that you'll do if you take elementary organic with me. If you take elementary organic chem, we'll do this experiment in lab. We'll actually synthesize aspirin from salicylic acid and acetic anhydride. So for instance, if I said, okay, I have 11.6 grams of salicylic acid and unlimited amount of acetic anhydride, how much aspirin could I make? That's a question that stoichiometry can answer. So let's go through this one together. How many grams of ammonia are produced when 16.8 grams of nitrogen gas reacts with excess hydrogen gas? Excess means you've got a lot, right? So if you see the word excess, that just means you've got a vast quantity. But I've only got 16.8 grams of nitrogen gas. So the first thing you have to do is you have to write a balanced equation, right? Because you can't do step 2 of stoichiometry if you don't have a balanced equation. Excuse me. So let's go through the process. All right, we write our balanced equation. Now here's what I recommend that you do. I really recommend that you list the mass that you were given in the problem underneath that substance, and then put a question mark with units under the substance you're looking for, okay? That way it kind of organizes everything visually for you. You know, I've got 16.8 grams of N2, so I don't accidentally plug it into the wrong substance, and I'm looking for grams of NH3, okay? If you do it this way, that keeps you organized and you won't accidentally use the wrong substance when you're not needing to. So in other words, is hydrogen gas going to even be part of our calculations? No. So we're just ignoring it, right? So if you list what you know and what you're looking for, that helps you stay organized. Now, step 1, I guess you could think of that as step 0, right? There's step 1, where we're going to convert grams to moles of my starting material. I gave my starting material as 16.8 grams. Got to convert that to moles. So what do I use? Avogadro's number or molar mass? Molar mass, right. Nitrogen is 14, and there are 2 of them, so 28, right? Grams went on the bottom because I'm converting grams to moles. Questions on step 1? Just converting grams to moles. Yeah, I'm pretty sure that's the answer your that's the calculator give you. One of the things that I want to point out, we always carry extra decimal places here and round at the end, okay, because we don't want to accumulate a rounding error, but this is the actual value your calculator gives you. It's 0.6, okay, so that's not a rounded value. So make sure you know you need to carry out extra digits here, and then we'll round our final answer to 3 sig figs at the end, okay, because don't round to 3 sig figs here, and then round your next answer to 3 sig figs, and then round your next answer to 3 sig figs. Okay, you round once. So don't let that throw you off, because you're looking at that going, well, that's got 2 sig figs. Well, the reason, that's not a rounded number. If you do that in your calculator, you get 0.6. Okay, so that's not a rounded value. So there's step 1. Everybody good on step 1, grams to moles. Now we're going to take that answer, and we're going to multiply by the mole ratio. So if I want to go from moles of N2 to moles of NH3, is N2 going to be on the bottom of the conversion factor or on the top? If I'm trying to get away from N2, where's N2 going to go? It's going to go on the bottom, right? So the coefficients go right here, right? There's 1 N2 for every 2 NH3. So I'm taking 0.6, multiplying by 2, and dividing by 1. Again, you would carry out extra digits, but 0.6 times 2 is 1.2. There's no extra decimal places to carry. So the unit that you're trying to get rid of goes on bottom. Unit you're trying to convert to goes on top. And these numbers are the coefficients from your balanced equation, which is why if your equation isn't balanced, you're kind of up the creek. Now my unit is moles of NH3. Does this make sense? Okay, so there's step 2. Now we're going to take that moles and convert it to grams, because that's what the problem asked for. Okay, so molar mass, I just rounded it to 17. It's actually a little bit longer than that. So I took that number of moles, multiplied it by the molar mass. Now I round my final answer to 3 sig figs. Okay, this is where my final answer gets rounded. I had 3 sig figs initially. The 16.8 has 3 sig figs, so my final answer has 3 sig figs. We don't include sig figs for molar masses. We're treating molar masses like constants, okay? And then don't forget your units would be grams. Questions on how we do this? 3 steps. Step 1, step 2, step 3. If you follow these 3 steps, you'll always get it right, assuming that your equation is correct, right? You have to have a balanced equation, and assuming that your molar masses are correct. Okay? So, you do this one. What mass of water is produced when 14.2 grams of oxygen gas reacts with excess hydrogen gas. And I am going to pause the recording for this. All right, let's go over the answer. So the first thing you have to do is you have to write the balanced equation, right? Is oxygen gas monatomic or diatomic? Diatomic, right? And hydrogen gas, monatomic or diatomic? Diatomic, right? So you have to write your balanced equation. And then list what you know and what you're looking for. We're given 14.2 grams of oxygen gas. Excess hydrogen gas, we want to know what mass of water we can produce. Okay, so we list what we know and what we're looking for. Then we're going to convert grams to moles. Okay, so carry out extra decimal places. You can round at the end. Questions on this step? I should have probably carried out another digit there. 0.44375 is what my calculator gives me, so I probably should have carried out more digits. Everybody good on this step? Okay, now we're going to do the mole ratio step, right? So the mole ratio is 2 to 1, because if there's no coefficient, the coefficient is 1. Okay. So 2 moles of water are produced for every 1 mole of O2 that reacts. So again, I probably should have carried out more decimal places here. Just start running out of space on the slide at some point. Everyone good on step 2? Mole ratio comes from the balanced equation. All right, now the last thing we're going to do is we're going to take that number of moles of water and convert it back to grams. I rounded the molar mass. Okay, I rounded my molar mass. Yours is probably 18.01 something. But my final answer is 15.9 grams. It shouldn't affect the final answer. Do we agree? Did you come up with the same answer? If you got 16, but it was because of rounding differences, that's not going to be a problem. If you come up with 16.5, that is a problem, right? That's not rounding. That's bad math. Questions on this one? Did you get it right? All right. Now, when you're good at this, okay, when you are good at this and you're good at each individual step, you can do it as one long calculation. This is probably what you saw in high school. A lot of students come to college and like, I hate stoichiometry, because they only saw this. They never saw it as 3 individual steps. And so if you can't do it as 3 individual steps, then doing it like this is not going to work for you. Okay, so I only recommend doing it this way when you're good at each of the 3 steps individually. Okay, so here's step 1, I'm converting grams to moles. Now here's step 2, multiplying by the mole ratio. Now here's step 3, converting moles to grams. Okay, but I only recommend doing it this way when you're good at it as 3 individual calculations. Because if you can't do the 3 separate calculations, it's going to be a train wreck when you do it this way. When you do it this way, you'll multiply straight across and divide up. So 14.2 times 1 times 2 times 18 divided by 32 times 1 times 1. Okay, so multiply all across, divide straight up. Again, if you're not good at the 3 separate steps, don't do it this way until you're good at doing step 1 independently, then taking that number and doing step 2 as a separate calculation, and then doing step 3. Okay. Once you're good at that, it saves you a lot of writing to do it this way. You don't have to write as much. But only do this once you're prepared appropriately. Okay, here's one for you. Read it to you and then I'll pause the video. Potassium carbonate reacts with barium chloride. Write a balanced chemical equation. How many grams of the product that contains carbonate are produced by 1.89 grams of potassium carbonate? I'll pause the recording and then I'll give you time to work. Let's go over this one. So the first thing we need to do is you have to write our formulas, right? You have to write formulas, we have to write a balanced equation. What kind of reaction is this? Double displacement, right. So this is why we have to write formulas, right? Because you can't write an equation without formulas. So check your formulas. Did you get them right? So potassium's going to get together with chloride, and barium's going to get together with carbonate. So there's our final balanced equation. 1, 1, 2, 1 are the coefficients. Do we agree? All right, now we're not interested in anything but the potassium carbonate, right? Because we're given this mass, excess of this, and we're not interested in potassium chloride, we're interested in barium carbonate. Okay, so we want to know how many grams we can produce. So we're going to convert grams to moles using the molar mass. I came up with 138.211. Did you? Something similar? So there's my conversion factor. Carrying out extra decimal places. Do we agree? Questions on step 1? All right, now we're going to use the mole ratio, which is 1 to 1, right? Mole ratio is 1 to 1, 1 mole here to 1 mole here. So my number doesn't change, just my units. Even though the mole ratio is 1 to 1, I still want to see this step in your work because I want to know how you converted units from moles of K2CO3 to moles of BaCO3. Okay, so even though my number isn't changing, I still want to see this step so that I can know that you understand how to convert those units. Okay, so please show me this step. Okay, I am going to be looking for it. I need to know how you got from one unit to the other. Questions on this step? Number doesn't change, only the units. Now we'll convert those moles back to grams. So I came up with a molar mass of 197.341. Rounding my final answer to 3 significant figures gives me 2.70, and my units would be grams. Check your work. If you made a mistake, do you see where you made it? Does anyone need me to go back to any of the first 2 steps? Questions, questions, questions. All right, here's one more for you to do. Propane is a common fuel used for cooking and home heating. What mass of O2 is consumed in the combustion of 1 gram of propane? Pause the recording, and then I'll give you time to work on this one. All right, last problem. So, first of all, you need a balanced equation. Right? Coefficients are 1, 5, 3, 4. This is a combustion of a hydrocarbon, so our products are always CO2 and H2O. If we were combusting a metal, right, that'd be a metal oxide, but if we're combusting a hydrocarbon. So we're getting CO2 and H2O. All right, now here, look at what the problem was asking. It says, what mass of oxygen is consumed? All right, this is what I'm saying. You don't have to do stoichiometry about a product from a reactant. You could use a reactant to figure out how much of the other reactant is getting used. Okay, it doesn't necessarily have to be a reactant figuring out information about a product, or a product figuring out information about a reactant. It could be a reactant figuring out information about another reactant. If I have 1 gram of propane, how many grams of oxygen gas will it react with? All right, so I did it as one step here. You should get the same answer either way. Right? You're converting grams to moles. That's step 1. The mole ratio is 1 to 5. For every 1 mole of propane, I use 5 moles of oxygen. And then moles back to grams. So if you were doing it this way as one long calculation, this is what it would look like. If you're doing it as 3 separate calculations, you have this calculation, take that number, do this calculation, do that, take that number, then do this calculation. You should get the same answer either way, 3.63 grams. 3 significant figures. Questions on this one? Always ask yourself if your answer makes sense. Right? You always have to ask yourself if your answer is reasonable. If you come out with an answer like 360 from 1 gram, that's probably not a reasonable answer, right? You've probably got a conversion factor upside down somewhere. So always ask yourself if your answer is reasonable. Questions on this one? All right, so that's where we're going to stop for today. On Monday, we'll do limiting reagents, which is just stoichiometry 2.0. And I hope you have a great weekend.